So today's webinar is entitled Overview of the Intergovernmental Panel on Climate Change Special Report on the Oceans and Cryosphere in a Changing Climate. It will be provided by Hub researcher Professor Nathan Bindoff from the University of Tasmania. Professor Bindoff has had a long and extraordinary career in ocean and climate change science, beginning with some of the first papers and methods for analysing the changed and changing state of our oceans. With students, Nathan discovered the acceleration of the water cycle from ocean salinity measurements due to climate change. He made the first estimates of the high melt rates of the Antarctic ice sheets by the oceans and wrote some of the first papers on the human influence on the oceans. Nathan has had important leadership roles in the 3 rounds of the IPCC assessment reports and contributes to the Earth Systems and Climate Change Hub Project 5.7, Tracking Ocean Change, and ocean observations and models. So I'll pass over to Nathan now. Just a reminder, if your video is on, if you wouldn't mind turning it off, and to pop those questions throughout the webinar into the chat function of Zoom. Great, over to you, Nathan.
Oh, look, thank you very much, Sonia. It's a pleasure to be giving a seminar to so many people. It's amazing. So what I'm going to do in the next 40 or 50 minutes is really give an account of my view and some of my colleagues' view of the key messages and results that came out of the Ocean and Cryosphere in a Changing Climate IPCC report. And this IPCC report was released on the 25th of the 25th of September 2019. And its release culminated after the approval of the summary for policymakers. That summary for policymakers is actually the key part of this report, and it has the key messages. It took 4 days and about 300 to 400 people to actually agree line by line, word by word, every statement in that summary for policymakers. And I have to say, actually, it's an extraordinary experience to be in one of these IPCC approval sessions. And amazingly, the final document is actually better than the one that went into it at the beginning. So let me sort of run you through what the SROCC report, the Special Report in Oceans and Cryosphere in a Changing Climate, was about. This report was actually commissioned about 3 years ago by a variety of United Nations governments. It was commissioned on the basis of having an oceans section. There was also a separate requirement to look at the cryosphere. There are many emerging risks coming from the changing cryosphere. And also there was a request from governments to look at high mountains. So this report brought all of those things together. So it covered the oceans, covered the changing cryosphere and high mountain regions. And that is really the content of this report. And you can see in this front cover here that the report covers the deep ocean, the polar regions, through to the tropical shores, through to the coasts and shallow oceans, and in addition, the high mountains. The report covers all the aspects of water on the planet, from the highest mountains to the deepest oceans, from the equator to poles. And we actually ordered this report to work from the high mountains to the deepest oceans, but we've also added in the risks of extremes and abrupt changes, which is actually a very strong and emerging subject. So this slide just shows us the overall structure, and so if you're wanting to look at the report and you have a particular interest in the polar regions, you would look at Chapter 3, for sea level rise and the implications for low-lying islands, you look at Chapter 4. For the chapter that I led with 14 other people, you look at changing ocean, marine ecosystems and dependent communities. And then for this emerging subject around extremes and tipping points and abrupt change, not only in the physical system, but actually human communities, you look at Chapter 6 as well. One of the things that is the hallmark of these special reports, which is really quite distinct from the other IPCC assessments, is that these special reports cover not just the changes caused by rising greenhouse gases on the physical system, but they also cover how that will impact on marine ecosystems overall, and human systems, and the communities that go with these. So these are transdisciplinary reports, and that's actually one of the advantages of the reports, but it's also one of the things that makes the reports pretty complicated to deal with and implement and to draw out the key messages. These are these IPCC reports are famous for the level of collaboration, for the level of engagement, and this special report, while not the largest, is no exception to this rule. There are a total of 104 authors who are selected on the basis of their expertise. And in addition to those 104 authors, there's a group of people who are contributing authors, and there's another 300 to 400 of those. So this report has engaged with the oceanographic and cryospheric and high mountain communities to the tune of about 400 to 500 people. The formal author team is very carefully selected, includes full range of diversity and gender, and we have 31% of women, early career, senior researchers. Those authors come from 36 different countries, so a cross-section of the developed and developing world. And these reports are, and I've been participating in 3 of them, are escalating in each new report. And even this special report has just under 7,000 different studies involved. And each report, and this one is no exception, goes through 3 rounds of independent assessments from experts as well as actually government reviewers. And in total, there were 31,000 different comments. Every comment, by the way, is actually published at the same time as the release of the formal report. And as a consequence, you can actually track our responses, the author's responses to the comments, through the 3 formal rounds of review to see how the authors responded to the report, to the comments from reviewers and governments, and to understand whether the report was reshaped by those comments and advice from experts. And for those who know Jeffrey Sachs, a famous economist, this is the thing about IPCC reports. They're fantastic, mobilising the research community at the science policy interface to actually create an assessment. And in this case, the assessment is of the changes in the oceans across those different systems. Australia is a major contributor to these IPCC special reports, and here we have CLAs and lead authors. There were 7 Australians distributed across Australia, and we even trained another 21 different contributing authors progressively over the course of 3 rounds as we needed their expertise to support the underlying literature. The 5th assessment report, which was released in 2013 and 2014, basically summarised up much of the knowledge that we had at the time around the overall system. We understood in the 5th assessment report that the ice sheets, Antarctica, Greenland, were actually losing mass to the and hence transferring mass to the oceans and causing sea level to go up. We understood that the glaciers were losing mass and were also transferring mass to the oceans through river flow and causing sea level to also rise. We understood that snow cover in the northern hemisphere was actually reducing and had been attributed to human influence as well. We understood that permafrost was actually declining and that the Arctic sea ice was actually declining. In the case of the Antarctic, there was inconclusive evidence on the basis of the understanding science at the time, and so our confidence in the understanding of the very slight observed increase in Antarctic sea ice was not well understood. So the message from the fifth assessment report was that there was some tremendous large-scale changes going on, but there were also some small conundrums as well. And in the ocean, we had rising heat content, a decline in ocean pH, a decline in oxygen, and this report talks a lot more about oxygen over the fifth assessment report because the evidence is a little bit stronger around that, and this report reports very strongly on new sea level information, particularly around extremes and the conversion of the historical century extreme, the 1 in 100 year event, into annual events, and also the emergence of what's become a hot research topic around marine heat waves. So we understood most of this sort of thing in the fifth assessment report, but this report is building on that knowledge, and there are sustained new and strengthened messages that have come out. Perhaps a key thing, if I was to have a glib single line around this report, is that the world's oceans and cryosphere have been taking heat from climate change for decades. Taking the heat. It's a lovely pun on the fact that the oceans are absorbing 90% of the energy imbalance in the surface of the Earth and taking up the heat, and consequently reducing and slowing the rate of surface temperature change. But the consequences for the ocean and for nature, and as a consequence of our understanding of the impacts on community, are profound and sweeping. I talk about the polar regions. The polar regions actually have quite a distinctive, different characteristic change from the mid-latitudes and equatorial regions. And so they're actually a really good region to talk about separately from the rest of the global oceans. The polar regions are actually perhaps some of the only regions in the world where there are positive impacts from climate change. The Greenland and Antarctic ice sheet masses are losing mass, and actually it's accelerating. The rate of mass loss by Antarctica and Greenland has nearly doubled, and we have actually committed to long-term global sea level, and I'll illustrate a really nice example of that long-term commitment that comes from the melt of the Greenland and Antarctic ice sheet. There are interesting shifts in the Arctic sea ice and its character. It's declining every month, and it's also getting thinner. And small temperature changes really make a difference. At the global level of warming of just 1.5 degrees, which the report from 2018 on the 1.5 degrees showed that it was possible to have. If we were to warm only 1.5 degrees, the Arctic Ocean actually would be rarely free of sea ice in the September, so the late autumn period, in the autumn period. At 2 degrees, actually, just a 0.5 degree difference, it will be frequently free, basically 1 year in 3. So small changes make very substantial differences in the sea ice in the Arctic region. It's already clear that humans have affected the Arctic and Antarctic polar region ecosystems, and there are consequences and impacts on that on resource-dependent communities with global implications for food provision in those regions. This schematic, which actually features, is a summary in one of the boxes in the polar oceans, illustrates some of the different changes that have occurred in the Southern Ocean. What you can see here is a slice through the global ocean. This is South America, Antarctica, Australia, Africa. Nearly everywhere in the global oceans, the surface temperatures have warmed up. But curiously, actually, the south of the biggest current in the world, the Antarctic circumpolar current, it's actually very slightly cooled, and it's also freshened. So this is counter to our normal thinking around climate change for the mid-latitudes and equatorial regions. The winds have actually strengthened very significantly over the Antarctic, the westerlies, in part because of ozone depletion, but also because of rising greenhouse gases. It turns out that the Antarctic region is the source of dense waters that flow to the bottom, and the volume of this dense waters caused by really extreme conditions against the Antarctic continent has actually decreased, and we're pervasively seeing warming in the deepest depths of the ocean, particularly in the southern hemisphere, in the southern hemisphere region compared with the northern hemisphere. And then, curiously, there are many things that we call eddies in the ocean which have actually increased in intensity, and there are theories that tell us that that increased intensity balances the extra stress applied by the winds, and it means that the strength of the Antarctic circumpolar current has remained constant. And it's this setting of changes, many of which are attributable to human influence, that is quite different from the equatorial and mid-latitudes of the global oceans. Sea ice, I mentioned before in the 5th assessment report that sea ice was unexplained, and it remains relatively unexplained. It's very likely that Antarctic sea ice exhibits no significant trend over the period of satellite observations. There's low confidence in the ability of the current generation of models to reproduce the explained observations. And the other thing that is interesting and important is the Southern Ocean has a preferential way of taking up heat, so much so that actually 35 to 40% of that heat is taken up in the Southern Ocean, whereas it's only occupying 25% of the global ocean area. And that heat uptake by the global ocean by the Southern Ocean has actually increased since 2005. The Southern Ocean is not just about the physical system, it's also about key ecosystems, you know, the upper water column, kelp forests, rocky shores, deep sea, polar benthos, and ecosystems associated with sea ice, and also services that go with those. The Southern Ocean and the Arctic all have fisheries, tourism, and habitat services and transportation. And the thing that sets the polar regions apart is the fact that both the Arctic Ocean and the Southern Ocean have different characteristics relative to the rest of the global ocean regions, particularly in the areas of fisheries, tourism, habitat services, and transportation, where we actually have positive impacts on the system, whereas almost everywhere else we have negative impacts on the system with varying levels of confidence. So the Southern Ocean and the Arctic are quite distinct in their responses and the opportunities, if you like, for tourism and fisheries, as distinct from the other more lower, more equatorial mid-latitude systems. This figure, taken from the polar region chapter, just illustrates the overall messages. The system is being driven by ocean warming, acidification, the changes in the ecosystems through regional sea ice change, and because of the decline in sea ice, there's increased light, and from winds, increased iron, and a reduced ice shelves. And the marine ecosystems, in many ways, some of them are negatively impacted, some are actually have a mixed impact, and some are actually very positively impacted with the increases in light. Phytoplankton have greater productivity, macroalgae and penguins and phytoplankton in the ice shelf regions are also blooming. So what this figure kind of sums up in a very interesting way is that the responses in the polar regions have a complex set of responses in the marine ecosystems and consequently in the human services that go with those. But importantly, they have been observed and drawn out of the evidence from that enormous amount of literature that I talked about earlier. If we move from the polar regions to thinking about sea level rise, the melt of Antarctica and Greenland are big contributors to rising sea level. There's about 680 million people who live in low coastal regions. There's another 65 million people who live in the small island developing states. And all of these communities are vulnerable to changes in sea level and sea level rise from as far away as Antarctica and Greenland. It illustrates the idea that the world is very much connected to the polar regions. One of the results is an update of the contributions to the sort of rising mean sea level around the world from the present in 1950, more or less, through to 2300. And one of the astonishing things in my mind that occurred during the meeting, during the 4-day plenary session of the Summary for Policymakers, was that the governments demanded, didn't insist, they demanded that we don't cut off this figure of the future sea level rise for low emissions and for high emissions at 2100, but that we actually include the full record through to 2300. And what the governments were telling us is that they need to know what the future sea level rise is, even if the scientists think it's highly uncertain. And it is highly uncertain. That's why there are these vertical striations on the future projections. But the amount of sea level rise in a high emission scenario is quite extraordinary. It's actually more than 5 metres, can be more than 5 metres by 2300 for a high emission scenario. For a low emission scenario, the difference is quite striking. It's shown by this lower line with an extreme sea level of about 1.2 metres. So it's important, this interaction with the governments and the refinement of the figures that actually appear in the summary for policymakers. These levels are extraordinary by 2300. The new information we have is the sort of refinement of our estimates of the mean sea level rise and our understanding of the drivers. It's become increasingly obvious and that the ice sheets are playing a bigger part in the total amount of sea level that's being observed now. The contributions from Antarctica, Greenland, and through glaciers is actually much more than the contribution of the thermal expansion of the water column caused by the heating of the water column. So So in the third assessment report, it was thought that actually sea level was being basically entirely driven by thermal expansion and heat uptake by the oceans. But that's not true anymore. What's true is that actually the Greenland and Antarctic mass loss are as important as glaciers, and those three together are more than 50% of the total sea level rise that we're seeing in the present, and here is the present. And you can see that we're projecting from the 17 centimetres sea level rise as much as 184 centimetres of sea level rise by 2100 for a high emission scenario, and just half that, about 43 centimetres of sea level rise from low emissions by 2100. You might think that if we'd already observed if we'd seen 17 centimetres of sea level rise over the last century, that wouldn't matter much. But let me just illustrate how much that does matter and how much it matters going into the future. So RCP 2.6 is a low emission scenario, RCP 8.5 is a high emission scenario. And the historical century extreme event is a 1 in 100 year storm surge. Now, you can work out when that 1 in 100 year, the historical century extreme, will become annual event. And for some places, if you're in black, it's occurring annually. And you can see that in the Western Pacific, for instance, in these small island developing states, that they already, whether it's a high emission scenario or a low emission scenario, we're already seeing the 1 in 100 year event occurring annually right now. So that 17 metres of global sea level rise over the last century is already shifting the risks of inundation for these low-lying small island developing states, and similarly in the Indian Ocean and parts of the Americas. It's very clear if you look at this, and IPCC does this all the time, the high emission scenario leads to earlier times, much earlier times in many places. It's highly regionally variable depending on the circumstances of the particular region, the strength of the tides, the strength of wind surges. It's highly variable, but they're clearly occurring at earlier times relative to the low emissions trajectory, where many of the colours will be further into the future. We can answer the policy relevant question by actually asking how much would you put off building, accommodating the changes in frequency of sea level extremes by choosing different emission scenarios. And in the case of some regions, like around Japan, you can actually, the high emission scenario will be more than 10 years earlier, also in the high latitudes of North America, around Europe. And what you can see is that actually in many regions, the difference is much less in time, in part because actually those changes have already emerged. So this is where the 1 in 100 year event is actually less than 10 years different, because actually it's already occurring in the present. So what you can see is that we can make informed decisions, more informed decisions around how you might plan for your response or adaptation to the 1 in 100 year event becoming an annual event. So let me just summarise up some of the chapter messages from the polar regions. During the 20th century, sea level has risen about 17 centimetres. This is unchanged, but actually it's very clear that sea level is actually accelerating more than twice as fast as it used to be, and will accelerate this is in observations, so in instrumental record, and it will accelerate further, and we'll have a high sea level of 1.1 metres by 2100 without an emissions reduction. Extreme sea level events actually become very common across the world by 2050. Many low-lying coastal cities are exposed to flooding and land loss annually by 2050 without strong adaptation. And this chapter actually talks about the adaptive responses that we can do, and they range. They're very locally dependent. Protection of the coastal environment, accommodation by lifting structures up above the rising sea level. There are ecosystem-based sorts of defences that can protect the coastlines within certain limits. There's coastal advance by building walls further out. And then there are managed relocations, migration to different places as some islands were lost. And you can imagine in some of the countries, this managed relocation was actually a repugnant idea. And that was expressed in the plenary session by some of the very low-lying islands. And it turns out that the intersection, and that's the beauty of these reports, they can look at the intersection of people and risk and hazard, and the highest exposure and vulnerability are often those with the lowest capacity to respond. The Oceans chapter is not about sea level, it's about the physical changes in the ocean, the marine systems, the changing ecosystems, the changing human systems like fisheries and tourism that go with that. And the changes are pervasive, actually. The ocean I've talked about is warming up, but the most important thing is that the observations sit in this line here. And even over the last 50 years, there are relatively trivial changes compared to the commitment that we've made on either a low emission scenario or a high emission scenario. The ocean has actually, in the observations, has warmed, and the warming has been unabated since 2005. There are clear multi-decadal trends throughout the ocean, and particularly in the southern hemisphere, as I talked about earlier. Because we're connecting to the ecosystems and to the production of life in the surface waters, it's really important to think about the stratification. And this report covers the stratification of the global oceans as a first and unique time. The stratification changes are really quite small, but they're very important. We've already stratified the oceans by preferentially warming the surface waters by about 2%. And projected to increase the stratification by 1 to 9% in the case of the low emission scenario, and I think it's 9 to 15% for the high emission scenario. And these stratification changes affect the surface productivity and the availability of nutrients for life in the surface waters to live from. And I'll show that in the slide after this one, because this slide just brings home the fact that actually, as we change the global oceans, the changes are not uniform in their information. We talk about the arrival of a new ocean state. And what we mean is that if you think of the variability like this, and the ocean is warming up, it comes through the natural variation indicated by that, but it then increases and passes out. And that's a new climate. It's a new climate relative to the understanding of internal variability. And ocean acidification is the first variable to emerge under this definition. And this line here traces the fraction of the global ocean which has emerged from the intrinsic internal variability to a new state here in 1900. In 1900, we'd already pumped enough CO2 into the atmosphere to affect the ocean acidification by 70% of the global ocean through to 100% in the year 2000. Sea surface temperature has been progressively changing its state as well, and 80% of the ocean by 2000 has actually emerged into a different climate state. And then we can see here that oxygen, which is declining in the oceans, has actually emerged by 2050 over 70% of the global oceans. And for nitrate and net primary productivity, they emerge more slowly and more progressively. And so what this means is that temporarily we feel the effects of ocean acidification first, the warming second, the changing oxygen third, the net primary productivity, and then nitrate third, and then net primary productivity last of all. And so we concluded that a unique new ocean states that we've never observed in the instrumental record across a broad suite of climate indices like pH, oxygen, upper ocean nutrient levels, and primary productivity. So just to summarise, the ocean has been taking up the heat, and we've committed to large changes. As the ocean warms, actually the mixing of the surface waters into the deeper water means that oxygen goes down, and we report on that. The increased stratification means it's harder for nutrients to feed the surface waters and provide sustenance for marine life. We've discovered, and it's a new science, that marine heat waves have become much more frequent and severe. There's a doubling already observed in the system. And these heat waves are the way that corals and kelp forests will be affected dramatically sometimes, and the literature reports that, and we assess it. The oceans, I'm happy to say, continue to take up CO2 as a key service, which would otherwise be stuck in the atmosphere. So I've talked about these physical drivers influencing the surface waters, the net primary production, the surface food webs, the total animal biomass, and the maximum fisheries catch potential. And if you look over here, and I'll just talk to the high emission scenario, and perhaps we'll just pick out one example, the total animal biomass. Total animal biomass, if you look at the scale here, if you look at the scale there, what you can see is that the total biomass in the region of the equatorial and mid-latitudes through this region here will actually, by the end of the century, relative to 1986 to 2001, decline by something like 30%, 20 to 30%. And importantly, because there's no striations here, all the models basically agree. So there are profound regions of the global ocean where there's very significant net loss in animal biomass in the upper ocean. And then high latitudes in the Arctic, and this is consistent with the earlier polar regions discussion, in the Arctic and Southern Ocean, we'll see an increase in the animal biomass as well. And this is how it would translate into our proxy for a sustainable yield, and that's the maximum fisheries catch potential. And if you look at this, you can see that actually the biggest declines often map onto the low-lying coastal countries, the small island developing states, or the more poorer countries in the mid to equatorial latitudes. And these changes will and have been already attributed in the observations to climate change. It turns out that the people with the highest exposure actually are the people with the highest vulnerability typically, and they often are the ones with the lowest capacity to respond. So it's the same for sea level. It also turns out to be the same in fisheries and total animal biomass in the ecosystems as well. So we have a conflation of hazards for the same populations, basically. And while you saw that these animal biomass changes have a latitudinal dependent, they also lead to a net global decline in the biomass of marine animals across the food web. And you can see here the change in maximum catch potential, our proxy for sustainable yields, declining as a function of atmospheric temperature, quite a linear relationship really globally. And by 2060, you can see a -8%. And by the end of the century, we have an expectation that the global biomass will decline by 15 and the catch potential by as much as 20, in a range of 20 to 24% by the end of the century. And the good thing about fisheries is it's already relatively well managed, and there are opportunities actually to make adaptation within the governance systems to minimise those risks whilst supporting a more resilient ocean. This is not true for all ecosystems because most ecosystems aren't managed. We also undertook in this chapter a sort of, for the systems, the marine ecosystems that do not have sophisticated models like a fish model in the comparison project, we took a slightly different approach, which is a risk assessment approach, looking at the climate-related hazards that drive through warming, acidification, deoxygenation, sea level rise as it impacts on the coasts, and extreme events which can create pulse events. And those pulse events can actually lead to the rapid collapse of some ecosystems in the presence of, say, a marine heat wave or in the presence of an acidity wave, or in the presence of a storm surge. And if you do an assessment, and you do an assessment across an extraordinary amount of literature around all of these different ecosystems, you can see the warm water corals, perhaps, and they're ranked here. What we present here is a ranking of the systems that have most vulnerability going to the decreased and least vulnerability. So the warm water corals, the great reef systems are right at the threshold between very high risks versus the low risks for the deep sea, relatively low risk for the deep sea benthos. What you can see is that we've already come about 1 degree of sea surface temperature. It's actually about 0.8, and we're starting to cross the thresholds of sensitivity that we understand from all of the research around warm water corals. There's a similar understanding for kelp forests, but with different thresholds. And here you can see the various thresholds that are indicated for the changing in the impacts on these particular systems, calibrated as a function of temperature. For seagrass meadows, for the epipelagic, that's the surface ocean system, the rocky shores, saltwater marshes, cold water estuaries, and so on, even down to the deep sea benthos. And you might ask, why the deep sea benthos? Well, it turns out the deep sea benthos depends very much on the surface drop of particulate carbon through to the ocean, and as a consequence of changing their primary productivity, they also very quickly see changes in their food supply in those deep systems. And you can see across all of these systems there aren't any positive impacts in the ones that we assessed. Typically they're negative impacts, but with varying thresholds. And as we warm the planet, you can see that the systems that will be most sensitive were the reef systems, and then the kelp forests, and then followed by the seagrass meadows and the aspects of the epipelagic. And progressively, with higher temperature changes under the high emission scenario, will actually affect all of these ecosystems that we actually assessed as part of this report. we are already seeing that the shifts in fish populations, the graphs I showed of changed biomass, were basically pointing to the movement towards the polar regions of the fish populations. We actually see their turnover rates accelerate. So there's a tendency for them to have shorter lives and actually their composition to smaller fish. All of these things affect the communities actually, and as a consequence, and we had in the earlier in the report, the changes in their nutritional health and food security, particularly in those dependent communities. It's clear that actually if you reduce pollution, you can help mitigate some of those damaging climate impacts. And it's very clear in the literature that the governance frameworks and the policy frameworks are the best avenue for actually reducing the negative consequences and actually offering opportunities for people to adapt. We showed in particular the changes in marine heat waves, and I'll just focus on one. This is the heat wave that was actually off the Tasman Sea. It's close to my heart. I live in Tasmania. But actually that heat wave also went with high floods in the north of the state, a summer spring drought, an exceptional spring drought, which led to shortages of power for the state, and it led to oysters, collapse of the oyster industry, and various other anomalies. That disaster was valued conservatively at $300 million US, $500 million Australian dollars of damage to the state of Tasmania, and probably worth more. There are policy insights that you get from these kinds of reports because they do look at the overlay of impacts. It assesses the exposure of vulnerable communities, and there are some lessons to draw out of it. And I'll just sort of summarise those up. It's very clear that in the options between high emissions and low emissions actually typically reduce the negative impacts, and as a consequence, they point to the fact, along with the earlier reports that we have from the IPCC, that there is a definite urgency that if we want to make the 1.5 or 2 degree temperature changes, then actually we have to be prioritising timely, ambitious, coordinated action, and to respond to even the changes in the environment, we need to address them with widespread, enduring changes in the coast to mitigate, in the coast and other regions to mitigate some of those negative impacts. If you look at the literature, it's very clear that many of the climate adaptation responses are local, and to make local adaptation responses, you have to empower people, you have to drive communities and governments to tackle all of these transitions on those human communities. And that's why evidence is essential, and we can often take that evidence and combine it with the scientific and actually Indigenous knowledge, and there are examples of that in the report. And if you think about it, if you want to do it in a consistent way, it becomes really, and because it's local, it becomes really important that education and climate literacy are at the heart of those adaptive responses. And we can show it in examples. This is a figure from a frequently answered question from chapter 5, and you can see coral reefs. In the case of coral reefs, changes in the ocean and cryosphere, ocean warming, ocean acidification, extreme events, ocean deoxygenation. They're the hazards that the coral will suffer. It causes coral bleaching, it erodes them away, it weakens them, and so it makes them more susceptible to storm damage. if we put in other pollution aspects, which are practices that are still carried out in some places, the consequences are the loss of biodiversity, there's a loss of yield, there's a loss of cultural values, there's a loss actually of coastal protection. So these are negative consequences from the damaging impacts. And we run through some examples of that in that frequently asked question. This graphic kind of illustrates the complexity of the inputs with the negative consequences that go with those. This figure I actually love, and in some sense it's incomprehensible, but what it's doing is it's kind of thinking, well, how can we look at the overall system and understand where we can help and where are the challenges. So whilst it's sort of out of scope of this report, we looked at marine renewable energy, ocean fertilisation, enhanced weathering, so this is to affect alkalinisation, restoring and conserving coastal vegetation. This is can be at a global scale, but it can be at a local scale, indicated by the squares. Marine protected areas at local scale, reducing pollution, hydrological regimes. You can look across all these and you can look at their benefits actually. Renewable energy is actually something we're very confident we can actually make a big difference on mitigation of climate. But across the other things like restoration of reef systems or conserving vegetation, we're actually much less likely to have an impact on mitigation. So renewables is actually more useful for mitigating than restoring vegetation. One of the strong conclusions of the report was that vegetation was going to only contribute less than 0.5% of emissions. But you can see that alkalisation, for instance, there are a lot of issues around governance. Can we actually overcome the governance challenges associated with some of these systems? So what you can see here is some of the trade-offs between the difficulty, the efficacy on the left-hand side, that's in the benefits, versus the difficulty in actually getting social licence to deliver and undertake them. And we have to undertake them all. So let me just conclude. The difficulties here, we're looking at building cooperation and coordination amongst the governing authorities. So it's complex because it's across spatial scales, and planning horizons, both temporally and across systems. Education and climate literacy at the heart of this, partly for monitoring and forecasting, but also for actually understanding how to adapt and accommodate the changes. And you have to build capacity in the community to respond to these things, particularly at local scales. So let me just conclude, because I'm running out of time. If you want more information about IPCC, here are some key websites. The report is now published. It's available to the public, and you're now starting to get a sense of what it covered and the scale of the research that went into it. And let me just finish off with the next final slide. Thank you very much.
Fabulous. Thanks, Nathan. I know you had a whole lot of information from a very long report to squish into just an hour, so you did really fantastic. Since we are running out of time, we'll just move straight on into some questions because we've got a whole range of really fabulous questions. So we'll probably go over the 1 hour that we've set aside for this webinar. So if you can hang around, we'd love you to listen to the answers to the questions. Otherwise, we understand if you have other virtual things to get on with. So the first question from Sarah, she's interested particularly in the range of discipline diversity in undertaking the risk assessments and identifying the ocean-based response options. So I think this is in terms of the participants in drafting the assessment report.
Yes, so it's an interesting question, right? There are 104 authors, there are roughly 15 per chapter. But actually what often happened was the authors who had similar expertise has banded together to undertake many of those risk assessments. The risk assessments in the sea level chapter, for instance, joined together to and drew upon the contributing authors as well. So very often we had not a single author contributing to those assessments, but groups of 2 or 3 or 4 contributing to those assessments. And then very often the assessments also included many papers, so there were distillations that were built into those risk assessments. So there was no single line of evidence typically for anything in this report. I hope that's answering your question. It's very diverse approach, and that's the beauty of it. It's mobilising that expertise for kind of joint assessments, discipline expertise assessments across the different fields, whether it's coasts, marine ecosystems, and so on.
Right, and Sarah just follows up quickly, and she just wants to clarify that the discipline diversity was within the sciences rather than extending to other disciplines.
So every chapter we had lawyers, so it's other disciplines. We had Indigenous knowledge people, we had social scientists, we had biogeochemists, we had biologists. So in fact, because each chapter is thin on a discipline, there was a definite need to drive groups of expertise across the chapters, and actually also from that wider community. So yes, there was breadth, and much more than just physical sciences.
Fabulous, thanks Nathan. Next, Joe asks, are there any further insights on the expected continued capacity of the Southern Ocean to take up carbon dioxide? As noted, the contribution of the Southern Ocean in heat absorption is very large.
Yeah, so there's a couple of papers on the temporal variability of carbon dioxide uptake. Actually, the uptake has increased in the last decade, contrary to what was published for the decade before. So the long-term answer is it will maintain its mean uptake in all probability.
Okay, fabulous.
Notice the equivocation.
Always. The next question comes from Maggie, who asks, did you notice any differences between the government approval session for this special report compared to earlier assessment reports?
So I've been through 3 assessment reports, and the first assessment report, and this was the first one which was across working groups. In the first assessment report, I do remember there were some very interesting blockages in the discussion, but they are actually resolved, and typically resolved on the plenary. In the second one, there was more breakout sessions, which resolved out of plenary but brought back to plenary. And then in the third one, what I noticed, which was the most recent one in Monaco, is that there was a more legalistic perspective in the session, and I hadn't seen that before. And the behaviour of some of the countries was quite interesting, in the sense that you almost felt we had barristers as some of the representatives. I don't know if they were barristers, but they felt more legalistic. It was clear also that, and I've never seen it before, that some of the poor countries or low-lying countries brought in expertise from developed countries. So that was a new experience for me as well. So developing countries taking a very strong interest in representing their interests in these plenary sessions, specifically brought consultants with them, and that was new too.
Fabulous, thank you. The next question comes from Molly, who asked, for the heatwave ocean slide, was El Nino and La Nina cycles included in the analysis?
Yeah, it's a very good question. The El Nino and La Nina cycles do modulate the frequency of heat waves, and that is understood as part of the analysis. And so we do, so they are formally taken into account, and we still get a very strong changing incidence of marine heat waves. Marine heat waves are relatively short events, 3, 4, 5 days, relative to the much longer duration of El Nino events. But they are taken into account and understood.
Great. And we have another question from Danny, who asks, how significant will the ocean... Oh, sorry, it just disappeared on me. How significant will the coastal cities, such as Sydney and Hong Kong, be affected by the increase in sea levels for the next few decades?
Yeah, so maybe there are many cities that are much, much more marginal than Sydney or Hong Kong. The Hurricane Sandy was a wake-up call for the Americans with the inundation of their subway systems, the extreme storm surge that went with that. And the numbers I was showing is that really that, well, not specifically, but it's actually in the slide that I showed, that those specific cities will see a dramatic increase in that return period. So if there's a storm surge that's one in a century that affected Sydney, for instance, that's going to be an annual event by 2030, 2040, I think, for the likes of Sydney. And in the case of Hurricane Sandy, that was actually a 1 in 100-year event, actually becoming, it'll be 1 in every 20 years at the moment, and it will emerge as an annual event in the mid 2030, 2040 timeframe.
Okay.
They're not trivial. The changes, actually, small sea level changes have big effects on sea level extremes.
Mm-hmm. Fabulous. We have another question from Ophelia, who asks, how do you account for the possible isostatic adjustments into these uncertainties after 2050? Was that included or not important in your question? I wonder if the isostatic movement is important for the estimation of sea level rise impact to islands near the boundary plate between plates, for example, Southeast Pacific and Australian plates. Start with that one.
Yeah, so isostatic rebound is taken into account. It's actually, in the case of isostatic rebound caused by the loss of mass off Greenland, for instance, and Antarctica, that's not associated with plate boundaries, but that is taken into account because we actually have models of the temporal history of the rebound global scales. It is actually it's a significant signal in some places. It's a relatively small signal in other places, but the short answer is it's taken into account. There's also uplift with each of the plates, so that's additional to the isostatic rebound from the ice sheets. And that's taken into account to the extent that it can be. And we don't always have good models for that. And so it will be part of the uncertainty in the changes in extreme and in the projections of sea level in particular regions. Those signals are part of the reason, along with the size of the tides, why the changes in extremes is so regionally dependent, whereas the global sea level is a much smoother variation globally.
Okay, and we have a follow-up question from Ophelia as well, who asks, for those areas defined as low, so less than 5 to 10 metres, what is the accuracy of the shuttle radar topography mission, and is this accuracy included in these predictions of sensitive regions to sea level rise?
Synthetic aperture radar, I think, is what you meant, Sonia. And actually, there's quite a bit of work on the accuracy of those measurements, because the transition from coast to ocean is actually quite difficult. relative to the open ocean. And we're discovering new signs, new circulations. So the short answer is yes, it's taken into account. It is, it appears as a wider uncertainty typically, but we frequently still make good projections, measurements of those fine-scale coastal changes. So I'll give a slight equivocation, but it is taken into account to some extent.
Okay, fabulous. We have an interesting question from Ana from El Salvador. She asks, how can we build resiliency for vulnerable communities living nearby cities with a constant rise in sea level?
Yeah, so that we talk about that in our chapter at some length. And the experience is it's about preserving many of the natural environments, cultivating mangroves or swamp marshes. All these dunes, all of these things provide increased resilience in the presence of extreme sea level. There are, of course, limits to which you can adapt and cultivate those nature-based solutions. If the sea level rises too fast, of course, it will overwhelm any effort you have to actually manage those nearshore coastal environments. So that is one way of doing it. And there's a strong literature on this. It works in many places, and sometimes, of course, a maladaptation, which is what I kind of hinted at, is where you actually pull them down because you want to develop the coastal zone in a way that's actually antithetical to their protection. So this is where the intersection of policy, development, and coasts really matters.
Yeah, fabulous, thank you. Another question that's come in is, how well are the major climate feedbacks factored into the GCMs or global climate models? IPCC projections do have a reputation for being on the conservative side. Yeah,
in the fifth assessment report, and just recently there was a paper in Nature, and in the fifth assessment report we actually assessed that on global scales, and recently in the Nature paper it shows that the projections from the climate models are actually very good for the historical period, surprisingly good actually, and they have remained very robust over time. That is to say that basically we're projecting the same level of changes over the last 30 years of these reports with relatively little variation. We have a formal method of testing the models and their capacity to describe the historical variations that we've seen, and we're getting increasingly better at actually analysing those models and understanding their imperfections. But the overriding message is actually they're surprisingly good in my mind. It turns out that the climate information, rising greenhouse gases, is actually the term with the most skill in predictions of future temperature, future warming, future sea level on a 10-year time scale, strangely. So the short answer is actually surprisingly good.
Okay, thanks, Nathan. We do have got a few more questions, but I think we might just end with one more. And I do encourage you, there's a mail box on the screen, info@nestclimate.com.au. If I haven't got to your question and you would like an answer, please do send your question to that inbox, and I'll ensure that I work with Nathan to get you an answer to your question. But for the final one from Max, he asks, why are mangroves so much less affected than warm water corals, while estuaries are in danger as well? Is there any ecosystem dynamics that we can understand involved?
Yeah, so that's a very kind of perceptive question. It's not a question really about ecosystems. It's actually a question about the physiology of mangroves and the physiology of warm water corals. Warm water corals, if you apply a temperature variation to them, it takes a very small variation before they will bleach. You apply a larger temperature variation to mangroves, they're much more resilient and to those temperature changes. And as a consequence, in the risk assessment figure, it's that sensitivity to changes in temperature plus other drivers, ocean acidification and so on, that means the risk threshold is much lower relative to mangroves. It's basically physiological response to temperature change. Mangroves are more robust than corals are to local short-term temporal changes in temperature. It's physiological.
Fabulous. Okay. Thanks, Nathan. I think we're going to have to end it there. We are almost 15 minutes over. So thank you for everyone who's stuck around for the questions. It was really fantastic. Some great questions. So thanks again to you, Nathan, for your fabulous and informative webinar, and for everyone who attended. Just a reminder that we do record these webinars, and they're always posted on the Earth Systems and Climate Change Hub's website, and an email will go around to provide the link to that. So if you've missed some, or you know someone who would be interested, please feel free to pass on the link. If you have any questions or inquiries about today's webinar or the Hub, please don't hesitate to contact us. The contact details are there on the screen. And finally, look out for the next month's Earth System and Climate Change Science webinar, which will be happening around about this time next month, looking at some new simulations from global models that have come out under the CMIC6 project. So thanks again for attending, and we look forward to seeing you at the next Earth Systems and Climate Change Hub Science webinar. Thank you.
Thank you very much, everybody. Thank you, Sonia.